The Big Bang theory was first proposed in 1931 by a Belgian Catholic priest, Georges Lemaitre. Although he didn't use the term Big Bang, he called it the explosion of the primeval atom. The term Big Bang itself was coined by Fred Hoyle, who didn't believe in the theory and had proposed an alternative steady-state model in 1949. He actually intended it as a derogatory expression. The theory has been developed and refined over the last 90 years to give us a theory which fits the observations as we see them today. This video, I'll focus on the evolution of the universe starting from 1 second after the Big Bang. The reason for this is quite simple. The details of this are pretty well agreed. But first, just a little bit of background. All material objects we normally encounter, that's ourselves, any objects we see, touch, feel, are made up of atoms. An atom consists of a positively charged nucleus surrounded by a cloud of negatively charged electrons. Atoms combine together to make molecules. In fact, this diagram is a little bit of an oversimplification. Each electron doesn't orbit in a nice, neat circular orbit. It has a probability cloud whose size and shape is determined by the nuclear charge and the value of 4 orbital quantum numbers. Also, the nucleus is absolutely tiny. It's 100,000th diameter of the atom. So if the atom was drawn to 100 meters in diameter, the nucleus would only be a size about a millimeter. All objects emit radiation. The hotter the object, the shorter the wavelength of the radiation. In fact, there's a mathematical relationship between the length of the peak radiation and the temperature, and it's given by something called Wien's displacement law. To get the wavelength of the peak radiation, you divide a number which is called by Wien's displacement constant by the temperature. And I've just put some examples here. If we have a temperature of 5,800 Kelvin, that's surface of the sun, the peak wavelength is 500 nanometers. That's in the visible light region of the spectrum. In fact, it's yellow light, which is why you see the sun is yellow. If we go to 20,000 K, that's a temperature of a star much hotter than the sun. Then the peak will be in the ultraviolet. Although they emit some visible light, most of the radiation is in the ultraviolet. Let's go up to 15 million K, so those are temperatures in the core of the sun. Then the object is hot enough to be peaking in the X-rays. And at 1 billion K, which I'll talk about later in this talk, we're really talking about temperatures in the early part of the universe. The peak radiation is emitted in the gamma ray region of the spectrum. Most of you will know that light is composed of little packets of energy called photons. The energy of a single photon is given by this expression, hc divided by lambda, where lambda is obviously the wavelength, c is the speed of light, and h is a number called the Planck constant, incredibly small number, and it was named after Max Planck, who was one of the founders of quantum theory in the early 20th century. Now, if we put the temperatures and wavelengths in from the previous slide, we see that on the surface of the sun, wavelength 500 nanometers, energy of a photon is 2.48. Now these numbers are in electron volts. Electron volt is 1.6 times 10 to the minus 19 joules. Incredibly small number because we're dealing with incredibly small things here. But if we increase the temperature, shorten the wavelength, we see that the energy of the photon obviously gets higher and higher. And mass and energy are equivalent, as many of you will know from Einstein's famous relationship E equals mc squared. So you can see that if we put the equivalent masses here, then the mass of a gamma ray photon emitted at an object of 1,000,000,000 degrees centigrade will be comparable to the mass of an electron. And finally, if we go to an almost unimaginable 1,000,000,000,000 degrees centigrade, then the mass equivalent of a photon is equivalent almost to the mass of a proton or a neutron. Okay, we've got the basics out of the way. Let's talk about the universe at 1 second old. We believe it was incredibly hot, 100 billion Kelvin. For instance, the inside of the sun is only 15 million. The region we see as the observable universe now, 92 billion light years across, was only 0.1 of a light year. It was a sea of protons, neutrons and electrons and neutrinos. No atoms, no nuclei, all moving at very high velocities. And there were dark matter particles. Neutrinos are the lightest known subatomic particle, 500,000 times lighter than an electron. They have no electric charge. Very fast moving neutrinos, moving close to the speed of light, have so much energy that they can interact with matter, such as a neutrino can smash into a neutron and convert it into a proton and electron, or the reaction can go the other way. Slower moving neutrinos, because of their low mass, don't interact with ordinary matter. So if we go back to when the universe was only 1 second old, it was radiation dominated. It was so hot and there were so many gamma ray photons with energies around 40 million electron volts. These completely dominated the mass of the universe. The universe was also rapidly expanding and cooling. And just after this time, something called neutrino decoupling occurred. This is when the neutrinos' energy fell to such a point that they could no longer interact with ordinary matter. Our current theories then predict that these neutrinos, which had decoupled from matter, have been freely passing through the universe unhindered ever since. There should be a cosmic neutrino background. In fact, this is a prediction of the Big Bang Theory, and it's a relic from the universe when it was 1 second old. Perhaps unsurprisingly, has never been found because it's extraordinarily difficult to see neutrinos anyway, and these neutrinos would have been slowed down by the expansion of the universe, making them almost impossible to detect. But in 2015, its existence was inferred by very small, subtle changes in the cosmic microwave background. As the universe continued to expand and cool, by the time it was 10 seconds old, it was 15 to 20 billion Kelvin. And that's cool enough for atomic nuclei to stick together without being blasted apart by collisions. This was the start of Big Bang nucleosynthesis, in which helium and other elements are made in the early universe. So this diagram shows two different routes to making helium in the early universe. The first one, the top one, hydrogen and a neutron combines to form deuterium. That's an isotope of hydrogen which has 1 proton and 1 neutron. The deuterium then combines with another proton to produce helium-3. So that's helium with 2 protons and 1 neutron. The helium-3 then combines with a single neutron to give us standard helium, helium-4. And at each stage of this process, a huge amount of energy is released. The bottom route, route 2, shows another way of doing it. In this case, the intermediate step is tritium, so that's an isotope of hydrogen with 1 proton and 2 neutrons, but the end state again is helium-4. Effectively, the whole universe was like a giant nuclear reactor. These are the reactions which take place in the centre of the sun to generate its energy, except that rather than taking place over billions of years, these reactions took place over 15 minutes. When the universe was 15 minutes old, it had cooled to 1 billion degrees. So this was too cold for this runaway nuclear fusion to occur. So the universe was frozen in composition at 73% hydrogen, 27% helium. There was a small amount of heavier elements such as lithium and beryllium, but these were only traces. And of course there was dark matter, which I'll talk about later. It was radiation dominated. Most of the mass was in energetic gamma ray photons. Each photon had an energy of around 400,000 electron volts. It was far too hot for individual atoms to exist. It consisted of a plasma, so this is where you have atomic nuclei and electrons. The observable universe was 10 light years in diameter. Over the next 380,000 years or so, the universe continued to expand and cool. Helium atoms formed from the electrically charged helium nuclei and electrons. Hydrogen atoms formed. So we moved from a plasma to a gas composed of neutral atoms. And the thing about a gas is it doesn't scatter radiation. So the universe became more and more transparent to radiation. And at around about 380,000 years, it became completely transparent to radiation. This temperature of the universe then was about 3,000 degrees, and it was, as I'll explain later, matter dominated by hydrogen, helium, and dark matter. The radiation we observe as a cosmic microwave background is a relic from this time. The microwave photons we see today in the cosmic microwave background were emitted from a spherical surface which now lies roughly 46 billion light years from Earth. Interestingly, the microwave background was predicted way back in 1948, but no serious attempt had been made to search for it. It was accidentally discovered by Arno Penzias and Robert Wilson in 1964 as a source of interference. Its discovery proved confirmation that the Big Bang theory is correct, because in the early 50s and 60s the rival steady state theory was popular. Okay, let's consider a volume V which expands by a factor of A to give a new volume V dash equals A cubed V due to the expansion of the universe. The density due to matter is simply mass divided by volume, and the density due to photons is simply mass in photons divided by volume, where the mass in photons is the number of photons times the average energy of each photon divided by c squared to make it into a mass. In our new volume, V dash, the density due to matter is simply mass divided by volume, so it's a factor of A cubed smaller. The density due to photons is the mass in photons divided by the volume, where the mass in photons is again number of photons times energy divided by c squared. However, the wavelength of each photon is stretched out by a factor of A due to the expansion of the universe. This means that the energy of each photon is reduced by a factor of A, which means that the photon mass is reduced by a factor of A, and the density due to photons is a factor of A to the 4 smaller rather than A cubed. So this means as the universe expands, the matter density falls as the cube of the scale factor, but the radiation density falls as the 4th power of the scale factor. So because the density of radiation falls faster than the density of matter, there's a time, roughly 50,000 years after the Big Bang, when the universe switched from radiation dominated to matter dominated. Over the next 100 million years, the radiation gradually got more and more redshifted, so became fainter and fainter. By the time the universe was 100 million years old, there was very little in the way of visible light. To an observer, it would have appeared completely dark. As the universe continued to expand and cool, matter began to clump together. When it was about 200–300 million years old, large clumps of matter existed which were around about 100 to 300 times the mass of the Sun. These clumps of matter contracted, getting hotter and hotter, and as they did so, eventually nuclear reactions started and the first stars were born. These early stars, which astronomers call population 3 stars, were supermassive compared to the Sun and shone extremely brightly for about 10 million years. This is a short lifetime compared to the Sun, which will last for about 10 billion years. They ended their lives in massive explosions called supernovae, in which the star was completely destroyed. These supernovae spread the elements like carbon throughout the cosmos. It's still not fully understood how galaxies, many of which contain hundreds of billions of stars, form. One theory which has gained strength in recent years is the bottom-up theory. According to this, the first galaxies began to form when the universe was around about 300 million years old, from lumps of matter including stars and gas clouds which had coalesced. Although we don't know what dark matter is, it plays a key role in this theory. Without it, the gravitational collapse to galaxies just doesn't happen in a reasonable timescale. As our universe continues to evolve, small galaxies are frequently gobbled up by larger ones. The Milky Way contains the remains of several smaller galaxies that is swallowed up during its long lifetime. In fact, the Milky Way is digesting at least 2 smaller galaxies even now and may pull others in over the next few billion years. The Milky Way is believed to date from just over 1 billion years after the Big Bang. Around the Milky Way is a halo containing old stars called population 2 stars, which don't have many elements other than hydrogen and helium. The small traces of heavier elements in them will have come from earlier population 3 stars. Because elements such as iron, oxygen and silicon are only present in minute quantities in these population 2 stars, they cannot be orbited by rocky planets such as Earth, Mars and Venus. The disk of the galaxy and the central bulge contain younger population 1 stars like the Sun, and these are much richer in heavy elements and are likely to have planets. The first population 1 stars appeared 8 billion years ago. Much of the material in the population 1 stars and the planets has been recycled. It will have been created in earlier population 2 and population 3 stars, which exploded as supernovae, scattering the debris throughout the universe. Some of this debris later clumped together to form stars and planets, such as our Earth. This phrase was taken from a book by the British popular science writer John Gribbin. We are literally stardust. Here's a few key milestones in the formation of the solar system, Earth and life itself. The Sun formed round about 4.6 billion years ago. Earth-Moon system a little bit later, probably around about 4.53 billion years ago. The first simple life forms emerged soon after the formation of the Earth, probably around 4.3 billion years ago. The first mammals 250 million years ago, and Homo sapiens itself emerged from the plains of Africa only 300,000 years ago.